Hello. Hi, everybody. Good morning, good afternoon, good evening. I'm glad to be here today. Let's start our meeting tonight. Let me open the file. Okay, we are going to cover design of experiments today. Only cover the first three sections because this is a more advanced topic, and so this week we shall have a project. So I don't we don't have time to get into the advanced topics. We'll just cover the foundational sections and material, including introduction, and then concepts from experimental design and factorial design. Okay, so what is a design of experiment? Design of experiment is the way we collect data, all right? Because in statistics, we are concerned with the analysis of data generated from an experiment. How do we collect data to answer our research questions, or what should our design be? It is desirable to take the necessary time and effort to organize the experiment appropriately so that we have the right type of data. Indeed. And sufficient amount of data to answer the questions of interest as well as clearly and efficiently as possible. So this is called this process is called experimental design. All right. So or some people call it design of experiments or experimental design. Either way, it refers to the same thing. Okay. What I will do is that I will use some examples to cover the concept. Okay. Here it says the variable that an experimenter is able to completely control in the DOE are called independent variables or treatment variables. These are called the input variables, explanatory variables, or factors. So in regression analysis, we call the independent variables. But here we call it treatment variables. Also, we refer to them as input variables or factors. Okay. And then independent variables that are known but non-manipulable are called nuisance variable. There are some factors that we cannot manipulate, so these are nuisance variables. Okay. All right. So with this, 1 second. With this, let's move on to an example. And wait a minute. Here is the noise. Noise is the effect of all the uncontrolled factors in an experiment. We will see what they are in terms of the formula later. 1 second. 1 second. Let me go back. Okay, for example, here in example 922, we see that in order to study the conditions under which a particular type of commercially raised fish reach maximum weight, an experiment is conducted at 4 water temperatures and 4 water salinity level. fish are raised in tanks with specific salinity levels and temperature levels. And there are 32 tanks, and one of the 4 temperatures and one of the 4 salinity levels are assigned randomly to each tank. The fish were recorded at the temperature of the experiment, and after 2 months. So then we will see each of the following elements, response, and factors, and factor type. Okay, to see what kind of combination, what kind of treatment. Here, with the 2 factors, the 2 independent variables, the control variables, each has 4 levels. So we have the 14, a combination of 14 treatments. The 14 treatments will become then together with 2 factors, each factor has 4 levels. We have 16 treatments. We shall determine which one randomly assign the experimental units, which are fish, into each treatment. And then we can study the effect of the combinational effect of temperature and the salinity level. Okay, so this gives you an idea about how design, what is a design of experiments, and how design experiment is controlled. Okay, and then you can extend this, apply this to many other scenarios, and the principle will be the same. Okay. So now we come and see fundamental principles, replication, randomization, and blocking. Okay. Replication means that the same treatment is applied several times to the same experimental units, or one time to several similar experimental unit. Okay, called the replicate units. Okay, so this is a replication. Let me move on. Then the block is a portion of the experimental unit that is more likely to be homogeneous with itself than with the other units. Okay. So using block, we can block the units that are more or less homogeneous. Okay. Because the experimenter uses information of possible variability among the units to group them in such a way that most of the unwanted experimental errors can be removed through the block effect. Okay. Let me see. And randomization is the process of assigning experimental units to treatment conditions in an entirely chance manner. So we know randomization will eliminate the bias. Okay. Okay, is to negate the effect of all uncontrolled extraneous variables. Usually, randomization is associated with design functions such as random sampling or selection, random assignment, and random error. Okay. So here we also see procedure for random assignment. So the number of experimental units, we have n of them, n, capital N experimental units. Then the randomization or random assignment of experimental units to treatment is that we use a random number table or statistical software to get a list of numbers that are random permutation of the number 1 to n. We can use R or Excel to generate that number. Then give treatment 1 to experimental units have the first R1 numbers in the list, and treatment 2 given to the next R2 numbers, and so forth until the last RK numbers, giving treatment K to the last RK units in the list. One example would be here. Okay, so we have two. Where we have one factor of 5 levels A, B, C, D, E of pain reliever. Then doses are administered to 25 subjects numbers, 1 to 25, with each brand administered to 5 subjects. So here we develop a design using the random assignment procedure. So we have A, B, C, D, E. In other words, how do we assign these 25 subjects with different doses level? And so we randomly assign these subjects to A, B, C, D, E without any order, all by chance. Okay. This is the concept of randomization. In other words, we do random permutation of the numbers by brand. Yeah. And you can see for the 5 treatment, each treatment has 5 subjects. Okay. For A treatment, we have 1A, 7, 12, and 10. For B, we have 25, 23, 4, 6, and 3, and so forth. All the 25 subjects were randomly assigned to these 5 treatments. Okay, there are another specific design, which we call randomized complete block design. It's a design in which subjects are matched according to a variable that experimenters want to control. That is, the subjects are put into groups which are blocks, because each block we have more or less homogeneous units or subjects, and they also have the same size as a number of treatments. So then the elements of each block are then randomly assigned to a different treatment group, so as to reduce the influence of unknown variables. Okay, let's take a look at this procedure. Okay, suppose we have K treatments and N experimental units, and we further assume that the experimental units can be grouped into B grouping containing K experimental units, so that B times K equal to N. We have B groups each group have k experimental units, then the following steps are what we do to conduct randomize the complete block design. So group of the experimental units into B group blocks, and each group containing k homogeneous experimental units. And in group 1, number the experimental units, okay, from 1 to k, and obtain a random permutation number 1 to k using a random number generator. Okay. Then in group 1, the experimental unit corresponding to the first number of permutation received treat 1. The experimental unit corresponding to the second number in a permutation received treatment 2, and so on and so forth. So then you repeat the steps 2 and 3 for each of the remaining blocks. Okay, so this is called a randomized complete block design. Okay, the difference between this randomized design and a randomized complete block design is that in a randomized complete block design, we block the group block the experimental units into B blocks first. Each block has k homogeneous experimental units. Then we do the randomization within each block. Okay, so instead of doing all the n experimental units in a completely randomized way from 1 to capital N, of course in this case is capital N equal to B times K. Instead of that, we do we do the randomization within the block. Okay, and then block by block we do the same thing. Okay, here let's look at the experiment example 924. Here we see that in order to study the number of hours to relieve provided by the 5 different brands A, B, C, D, E of pain reliever for pain resulting from different causes. Okay, 5 the brand pain reliever, and the headache, itch, and pain, muscle pain, and pain due to different reasons. Okay, and the bruises and so forth. Doses are administered to 5 subjects, each having similar types of pain. Create a randomized block design, or choose as blocks the different types of pain. So first, we have to block. Okay, block the types of pains because they are similar. They have similar types of pain. So we block these type of pain together. But then we randomly assign the experimental units within each block, whether it's a headache, whether it's a muscle pain, or pain due to cuts or bruises. Okay, so 3 blocks, but then each block, within each block, you also assign the experimental units, the same doses, the same randomly assign the members to experimental units to the treatments. Okay, so this is the idea. Of course, we talked about replication. there may be more than one replications within each treatment, within each block. So the idea can be generalized to have R replications of each treatment per block. Then they generalize the randomized complete block design with the K treatments, B blocks, and the R replications with capital N equal to KBR, which has KR homogeneous experimental units can be randomized as follows. So to extend the complete randomized block design with R replications case, make it more general, we let's see. Okay, we do it this way. Okay, group the members into B blocks. Okay, and now instead of K homogeneous experimental units in a block, you have RK because you have R duplications. Then and then group 1 number the experimental units from 1 to RK, and generate a list of numbers that are random permutation of the numbers 1 to RK. Then in group 1, assign treatment 1 to the experimental unit to the experiment having numbers given by the first R numbers in the list. Okay, and assign treatment 2 to the experiments having the next R numbers. Okay, next R numbers. So each time you randomly generate 1 to R. Okay, so then you randomly pick R numbers from 1 to the RK numbers within a certain block. Then you assign them to treatment 1. Then you randomly select the R numbers from the rest of the experimental units to treatment 2, and so forth. Okay, until every experimental unit is assigned an experiment. Then you repeat this for the remaining block the same way as steps 2 and 3. So let's take a look at an example. Okay, now we have use the same experiment, but we have what? Consider that example that doses for different type of pens. 3 groups of subjects are considered, with each group having 15 subjects. Group 1 consists of a subject with only headache. Group 2 of the subject with the muscle pain, and group 3 cuts and bruises. Of the 15 with headaches, now we have 15. Each group has 15 instead of 5. You see, so we have 3 replications. 3 replications for each doses. Okay, R is 3, and then K is 5, and then B number of blocks is 3. So you have then they are treated with brand A and so forth B, and so here's the way you replicate it. Okay, so you first choose randomly pick 3 numbers from the first 15 experimental units in a block. Okay, then you assign them to doses level A, and then when choose another 3 doses B, and then choose another 3 for C, and then okay. So wait a minute. H C, yeah. let me see, 1, 2, 3, 4, 5, 6, 7, 8. I think this table is not exhausted because each group is supposed to, let me see, oh, because it's each column is too long, so they cut it in two and put it side by side. Otherwise, you see 1, 2, 3, 3A, 3B, 3C, 3D, and 3E. Okay, and so forth for H. And then move on to block M. You have 3A, 3B, 3C, 3D, 3E. And then move on to C, cuts and bruises, 3A, 3B, 3C, 3D, 3E. Okay, so in each block, you have what? 5 treatments. And each treatment, you have 3 replications. Then the way you assign a replication is completely random. Okay, so this is how you work out the design. Okay, then we also talked about there's a special design called Latin square. Why Latin square? Because we use the randomized block design when we want to control a single source of extraneous variation, and there's only one factor of interest. When we need to compare K treatment means, and there are 2 possible sources of extraneous variation, then we have to use another design which is called Latin square design. Okay, is more appropriate. You know, in the previous example, we have what? We have the 5 treatment, which is level of doses. But here we may have doses, or you know, in addition to, we have two treatments. Okay, and we'll see an example. And here we see design definition 928 means K by K Latin square design. And then K rows and K columns. That means a row and a column each stand for a factor. Row stand for a factor, column stand for a factor. And each factor has K levels. So they have K rows and K columns. Okay, excuse me. And the K treatments are randomly assigned to the rows and columns. Okay, so that each treatment appear in every level and column of the design. Okay, so I will leave the history to you. So here, let's see how it goes. A gasoline company is interested in comparing the effect of the 4 gasoline additives A, B, C, D. Okay, and then on the mileage achieved per gallon. Sorry, 4 cars, 1, 2, 3, 4, and 4 drivers. 4 cars, 4 drivers are used in the experiment. Okay, so so how do you do that? We have different gasoline additive A, B, C, D, and okay, this is treatment, but we have 2 factors. Each factor has 4 levels: 4 cars and 4 cars and 4 drivers. So cars is a factor, drivers is another factor. So what shall we do? So you have 2 factors, and you have 1 treatment. You have 5 treatments. So the best idea is to use a square design, which called Latin square design. All right, so car as in the rows, drivers in the columns. Each has four rows or 4 columns. And so now what we do is that we randomly assign the treatments into the columns and rows in a way that no duplication of treatments for each column, for each row. Okay, so how does that work? So that works in this way. So you could so suppose you do DCBA, then you move then you bring A to the top and push everything down. You got the column C. Okay, and then you bring B to the top, put everything down. Okay, and you get a BADC. And you bring C to the top, put everything down. You get CBDA. In this way, you will create a square in which each cell, I would say, each intersection of columns and row is arranged in such a way that each row has all 4 treatments, and each column has all 4 treatments as well. So in this way, you will be able to do an experiment, collect the mileage per gallon to compare the different additive effect for car mileage per gallon, while not affected by the different drivers, by the different cars. Okay, in other words, you can still fairly compare the different additives, because all the different additives will be tested by the same car and same driver at least once. You can see car 1 use ABCD, right? ABCD. So you put all the different additives to car 1 at least one time, and you also put the additives to the different driver. For each driver will test all the 4 different additives one time at least, and then most 2. So in a sense, you will be able to compare the result. Okay, and let's see. Okay. What is the gasoline additive? What is this number? Let me see. Now, along with the Latin square, we can represent the corresponding observations. Number in parentheses are the gas mileage. Okay. Okay. So now here comes the test result. Okay. So you can see the first driver driving the first car use 18. The result is 18 miles per gallon. And when he drives the second car with C, 22, and so forth, different miles per gallon. Okay, so how do you compare? It will be so you will compare. So you will compare all the D's, take the average of the D, right, and take the average, and then and then take the average of all the C's, right, C's, and then B's, and then A, B, C, D. Okay, take the average and then compare the means. Of course, you need to calculate the variation and so forth. Okay, we are not going to get into the more details than that. I think it's a good point to stop. Yeah, as I mentioned, let me see, factorial design. 1.3. Okay, not yet. 9.3. All right. 9.3 talked about factorial design. Okay. What is factorial design? Factorial design is used to evaluate two or more factors simultaneously. Okay, in general, there are three ways to obtain experimental data: one factor at a time, full factorial, and fractional factorial. The most efficient design is fractional factorials. Let's take a look at one factor at a time. So one factor at a time. Here we see the two. Here in this example, 931, consider the following hypothetical data in which two types of diet, okay, fat or carbohydrates in two levels, high or medium, are administered for a week for a sample of individuals, okay. And at the end of the week, each subject was put on the treadmill and the time of and test the time of exhaustion in seconds, and then they were measured. The objective was to determine the factor level combination, okay, that will give maximum time of exhaustion. So you have two factors, each has two levels, and we have the different combinations: high or medium, medium or medium, medium, high, high, high. So like two coins, head or tail. Okay, two different coins, and then each has head and tail. So you have four combinations. And then each out of the four combinations, you have the four outcomes. Okay. Here is figure 9.1 is one factor at a time. So one factor at a time means you only look at the what? Okay, the factor level. Okay, combination for a one factor at a time at the approach of 931 is in 931. So example 931 is here, and 931 is here, and the one factor is that we look at fat, okay, by one factor, okay, at a time, or we look at the carbohydrate one factor at a time approach. But and then we can see from the result that there is no intersection. We draw this graph here. Okay, high, medium. We put all these in a graph. Okay, fat high, yeah, you can when fat and carbon hydrates are both high, the time to exhaustion is lowest. And then, okay, lowest. And they are both high, combination is lowest. Both high, fat is high. And this is fat is high, fat is high. Fat is high, carbon is high. You see, exhaustion time is low. When fat is high and carbon is median, fat is high, carbon is median. Fat is high and is median. It's larger. And the same way, when fat is low, you can see. So there is no interaction here. Okay. But then if there's interaction, okay, wonder what situation there's interaction. If the difference in mean response for different levels of one factor is not constant cross levels of the second factor. So if the two lines cross each other, then there's interaction. In this case, there is no interaction. They don't cross each other. Okay, 4 factorial design. Let's take an example. 4 factorial design. Okay. Wait a minute. 4 factorial design. Okay. One way to get the problem of interaction or in one factor at a time design is to evaluate all possible combinations of factors in a single experiment. This is called 4 factorial experiment. The main benefits of 4 factorial design is that every possible data point is collected. And the choice of optimum condition becomes easy. For example, in an experiment such as 922, where in the 922 conduct a 4 factorial design. And the simplest form of factorial design involves 2 factors only and is called two-way layout. A 4 factorial experiment with n factors, okay, and 2 levels for each factor is called 2 to the power n factorial experiment. You know, yeah, we have n factors. Each factor has 2 levels. Then you have to have at least 2 to the n power factorial experiments to be called 4 factorial experiment. Okay, it's practical if only a few factors, say fewer than 5, are being investigated. Beyond that, the design becomes time-consuming and expensive. Because what is what is 5? 2 to the 5 is 32. There are 32 treatments, and yeah, that could become more expensive and time-consuming. Okay. Okay. Let me see. Okay, I think this is a good point to stop. Okay, I'll post this recording on in the announcement for you to review. Okay, all right. If you have any question, feel free to contact me through messaging or discussion forum. Okay. Have a great day and great week. Okay. See you next week.